I will start recording now.
Berkeley time plus 3 minutes.
Okay. Seattle time then.
No, we are a little bit more punctual. At least this is the aspiration. So let's start. So before we start today at 3:30, there is a CART lecture given by Valkanen on incremental view computation. So very interesting. I strongly recommend that you either attend personal views online, but preferably in person. And today we have Hans Knoch giving our second invited lecture on another topic where he is a top expert on computing queries over 3D compositions.
All right. Yeah, thanks for having me again. And I will tell you an idea that is kind of it's very trivial in hindsight. It's like obvious in hindsight, but for some reason things were not presented this way when you read textbook database query optimization. And yeah, so let's get started. So let's start with a few warm-up examples. So suppose you have the following query, and I'm going to give you the query in RHEL, our relational AI query language, but it's pretty intuitive, so you probably can make out what it means. So let's say you would like to count, you have three singleton relations, R, S, and T, and you would like to count the number of triples, X, Y, and Z, for which X is in R and Y is in S and T is in Z. How do you think this should be computed? Joiner first. What's the best way to compute this query?
Multiply it by 9.
That's right, exactly. So we should just count the number of X in R, count number of Y's in S, count the number of Z in T, and then multiply the results, right?
By the way, Postgres times out on this. If you really try to compute the join first.
Okay, so this is, it's kind of an obvious thing that you would do. Let's make it a little more interesting. So same query, but now I would like, X is less than Y and Y is less than Z. What do we do now? I would like you to be the query optimizer. So, sort of a way to get you into the optimizer mindset. Go ahead.
Can you like count Z and then filter the other two and then count those and multiply them?
What do you mean by count Z?
Sorry, count the size of T, and then you can sort of filter.
Okay, so here you will need a little bit of a group by construct. So you could, here's one of the many ways to do this. You could count for every Y, the number of X's that are smaller than Y, and X is in R. Yeah, and then for every Y, the number of Z's that are greater than Y. So you basically, center your query at Y, and then you count the X side, count the Y side. And then for those Y's that do match, then you sum up the product. Yeah, does that make sense? So think of it as a tripartite graph. And so for every Y in the middle, you count the number of things that will match on the left, things that match on the right, and multiply the degrees together. Okay, now, so next query is no longer a sum product type of query, but let's say this is a maximum. So here we have three binary relations. are S and T, and they form a little path of length 3. So X, Y, and YZ and ZU. We would like to compute the maximum over this value U. So let's say this U is a floating point or whatever, an integer. And we project away Y and Z. So that's why Y and Z are here, but they are not the same as this variable U. U is something we are maximizing over. And then the group by variable is X. So for every X, you would like to compute the maximum U that is connected to this X. If you think about kind of a path of length 3, so from X to Y through R, and then from Y to Z through S, and from Z to U. And then you take for every X, what's the maximum value U that that X is connected to? Okay.
I have a question about syntax. Like looking at the syntax, how do you know that you're taking a max over U?
It's just the last variable. It's a convention. It's not an ideal syntax. It's kind of my least favorite syntax part of RHEL, because we could have put U, for example, like next to the max or something, right? Just to tell the difference between the two.
I was going to suggest a way of doing this, maybe, but actually that might be unscrewed anyway.
Okay, but we're going to play exactly the same trick. So what we do is we first going to compute for every Z the maximum U that it is connected to. Right, so that's W1 is the first intermediate relation. And then we will iterate over Y and Z, and then compute the maximum over Z. Right, so this is the second scan over the second relation. If you think about, in the graph sense, right, you are going from the variable that you are maximizing over, and then just keep accumulating this maximum until you get back to X. Yeah. So just one variable at a time to eliminate. So that's W2. And then finally, for every X, we'll be maximizing over the maximum value B that we have accumulated at this point from the other side. And this will run in time in linear time as compared to the quadratic time as before.
So what does it mean for W1 of Z and A if W1 is one, that's one error?
Yes. So the question was, over here, that doesn't seem to be a value A, and here there's an A. So it turns out when you take the max, you have to store it in a variable. So this is just making that more explicit, that for every Z, there's a maximum A that it is attached to. There's a different way to write this so that this, with a square bracket. Yeah, I just wanted to make sure that this A variable is explicit. Okay, so here's another fun one. So here is a graph query. So let's say E is the edge relation of a graph. And then we would like to count the number of patterns of this subgraph inside of a big graph. So imagine E being a billion, tuples in it. And we would like to count this pattern. We have a triangle, so AB, AC, and BC. And then off the edge of this triangle, there's CD and CE. So a triangle with a couple of edges pointing out of it. And we'd like to count this pattern inside of the big graph. And the question is, what's the best runtime that one can do? Okay, and so the solution would be something like this. So first, for every C, I'm going to count, basically the degree of the vertex C, because this V-shaped pattern, and there's no restriction. So I'm going to count basically the number of D and E's that can be connected to this. So that'll be something like TC squared, right? So TC times TC. And then we count the number of triangles. And we know from the worst case optimal join strategy that we can actually compute this query in n to the 1.5 time. The first query is only linear time because this is a degree counting query. And so the entire graph counting pattern can be done in n to the 1.5 because we just go through this triangle. So roughly that's the illustration of the idea of variable elimination. And things will get kind of much more interesting and non-obvious as you are presented with an arbitrary query. Okay, so the examples are meant to illustrate the following idea, that we kind of need a good way to represent the input to these problems, an algebraic abstraction to model these problems, because they all seem to be kind of answerable using the same type of idea. When you eliminate one variable, you take a max or you take a sum over a variable sequence. And then an algorithmic abstraction in order to kind of, have one algorithm to rule them all, which is exactly what the query optimizers do. Because in query optimization, is basically, it's an algorithm that will spit out an algorithm, right? The query plan is an algorithm. So you need an algorithmic abstraction to solve the query that comes from the algebraic representation of the input. Okay, and then finally, once we have that algorithm, then we need a way to find the best query plan. So that's the query optimization abstraction. So I will try to go through each one of these one by one. Okay, so let's look at some product queries. This is the abstraction that we'll be working with, and then later on we'll generalize this a little bit into functional aggregate queries. Those are a little bit more general. So some product query is the following query. So think about a conjunctive query that we have been discussing throughout this course, where we have the head of the query, and then we have kind of a existential quantification, right? And then there's a conjunction. The only difference in the sum product query is that OR becomes a sum and N becomes a product, and the sum and product come from operators of a semi-ring. It is precisely the same as a conjunctive query, except that sum and product are interpreted over a semi-ring. So the input to this query involves factors or functions or atoms or K relations. I think from the previous lecture you have seen K relations, right? So this is exactly a K relation. There is one K relation per edge in this query hypergraph. So for every edge in the query hypergraph, there's a K relation. Or in graphical models, they call this a factor in a graphical model. And then we are summing away, or we marginalize away some set of variables. So in database, this is called a projection. So we project away variables. In statistics, this is a marginalization query. So you marginalize away variables. Or existential quantification. There are many different words to describe exactly the same abstraction. And then the variables that we do not project away are the free variables. So these are variables in the head of the query. Okay, so here are some examples. So the simplest example is a Boolean conjunctive query, where sum is OR and then product is AND. And let's say we have one atom, which is the edge relation of a graph. So in this case, you can think of this edge relation as a function from pairs of vertices to true false, right? So EAB is true if A to B is an edge in the graph and false otherwise. And so the question of whether or not there exists a triangle in the graph can be expressed with the sum product query, where we want to say, does there exist A, B, and C for which this product is true? Right, so all three of them have to be true. Or, over the sum product semi-ring, we could ask, for instance, is there a path from A to B, B to C, C to D, for which A is different from D? right? And there's a group by variable. So here we also have a graph, and we're supposed to, for every vertex A, you would like to compute a path of length 3, where D does not go back to A. So one thing I want to point out is that here there's a factor. This is an indicator function, which is 1 if A is different from D and 0 otherwise. This factor is infinite in size. So it's unlike in this case where in order to represent this function, you can have kind of a finite representation. You can list all of the tuples in the relation, right? This relation is like a user-defined function. You know, it's something that's infinite. So in the formalism of sum product queries, it's entirely possible to have factors that are infinite. And there's a comeback. I will come back. I get back to this point. It's very important to allow for this so that our query language is much more flexible. Because without this, and you know, in database textbook, typically you will see these things are atoms and they are finite, and you apply the AGM bound or something like that. But that's not the case in practice. In practice, you always have natives and user-defined functions and things like that, and they are typically infinite in size. Okay, now the other thing is that this sum product query is really a great intermediate representation if you are going to implement a database engine. So consider implementing this as an IR, just like a relational algebra or it's an algebra, and you can use this to represent query plans. Okay, so now the thing that is kind of not talked about a lot in a Potts paper, for example, is how do you actually map from a query in practice into this representation? So you read my or you know anyone's Potts paper, we'll start with this query and then we kind of go off from there. But in practice, how do you actually map it to this representation to begin with, right? So I will give you a few examples, and then it will become really obvious. Okay, so for this query, if this was a count query, how do we map it into this IR that we supposedly we can optimize over after? So I'm going to abuse notation a little bit, and I'll define a function which has exactly the same notational convention as the relation. But this function is an indicator function. It'll be 1 if X is in the relation R and 0 otherwise. So think of R, S, and T as functions now. So then the mapping of this query, this is a completely equivalent representation of the query, but in the sum product form. So here we have sum over X, Y, and Z, and then R, and S, and T. Okay, so let's take something a little more interesting. Well, this is the same example as we had before. And here we have, R, S, and T, and then these indicators, these little indicator functions, right? Okay, so far everything is fine. Again, I want to emphasize the fact that some of these factors can be infinite in size. Yeah. So let's look at this query. So it's the same query as before, except that we are not counting anymore, we are summing. Okay? So here we are summing over this Z value. And now the question is, what is the corresponding algebraic, sum product representation for this query? What do you think it should be?
Just project over the ones you don't want, same as the last query.
Same as the last query.
Except you keep the one that you care about on the left-hand side.
So this is exactly the same query. The only thing I changed was that instead of counting, I want to sum over the Z, right? So there's nothing on the left-hand side. Everything will be, I mean, Q will be just a number, numeric number at the end.
Can you just remove this up? So make the X and Y.
Like here. You mean remove the sum over Z?
If you want to sum over Z, you would remove the other ones.
Yeah, so maybe the semantic of the query is not very clear to people. Yeah. I should have written this in SQL, but I suck at SQL.
So you
so-
want to project out the ones that do matches, and then you want to sum the projected value, is that what you're going to do?
So I want to marginalize away X and Y, just like before in the counting, right? But instead of counting, I want to sum over all of the Z. So
Do you multiply by Z?
you multiply by Z, exactly, yeah. So it's just like the previous query, except that you have to kind of multiply by Z at the end. Because the thing we're summing over is Z, it's not just a count.
As a point of clarification, like if you didn't have the sum over X, then the result would be, I guess,
A group by on X.
and the sum.
If we don't have the sum over X, then the group by variable is X.
Yeah, I will ask is that the Z type of Z is a integer, right?
Yeah, in this case, it could be anything as a floating point.
Yeah, but the summation, like, so that may also summation is what? Like the summation of it. Okay, in the previous slide, there's a token for summation of Z, right?
Mhm.
What's the token?
Yeah, so in this case, so the semantic of the count query is obvious, right? Which is, for every triple X, Y, and Z, add one. Yeah.
Like, so the RST and the indicators all return at the same value first.
Oh, you mean here?
Yeah, or RST and the indicators all return at the same value, right?
Right, so here
So
are,
if you multiply by Z, then Z should be in the same value, right?
that's correct, yes.
Yeah, and so
Yep.
what's the index?
Oh, I see what you mean. Yeah, so in the sum product semi-ring, I didn't specify the domain. So you could have natural number, integer sum product, you could have
Yeah, but
real
it's
number,
like
floating
Z
point.
should be-
That's right, exactly. Yeah. So the type of Z has to be the same as the domain of the sum product semi-ring. So this is under specified.
While X and Y, they don't have to be in the same semi-ring. X and Y.
X and Y do not have to be. X and Y can be strings, they can be anything. Yeah. Yeah, the thing that we are summing over will have to be in the domain of the semi-ring, and the things we are marginalizing away can be arbitrary. Okay, so yeah, so he gave the answer. The only difference between the previous query and this query is that I'm going to define the function t of z to be z times the indicator. So it'll take a value 0 if z is not in t, and it will take the value of z when it's in t. And then the query is identical. So this is the point I want to make, that the algebraic representation of the two queries are identical. They are the same. But they're not unique, right? You could have a different algebraic representation, some product representation. You could define a new factor, function wz, define it to be equal to z, for example. So you could have done that that way too. Either way is fine. Okay, and then the only difference when we change, a sum to a max is that it's exactly the same, except that now we are using a max product semi-ring. So in terms of the semi-ring, is pretty much, you can use it to capture a lot of the different types of queries. So max product or sum product. Note that in practice, you will see some ambiguity because max product is a semi-ring, max plus is also a semi-ring if the domain satisfies certain properties. And then sometimes there's some ambiguity into which semi-ring we are mapping things into. And sometimes both of the mappings are valid, but one will give you a better query plan than another. So that's kind of an interesting problem when you write a query optimizer. You have to figure out the optimal strategy, which semi-ring you are mapping into, and sometimes they can be nested inside of one another.
Can you fail the mapping semi-ring?
Can you fail? So
Like what if I wanted to max over, this might do like max over U minus Z or something in this case.
You know, just like really throwing a wrench into.
Yeah, so we do have kind of a fallback mapping, which is when I will define the entire conjunction to be one gigantic factor. Yeah, so it's, you know, it's not useful, but you can always map it to that.
Then you lose the ability to output.
That's right, exactly. So yeah, you cannot factorize or anything like that.
But just within that.
That's right, yeah. That's a part of the query, yeah. Yeah. Okay, so now that we have the algebraic representation of the query, let's try to optimize it. And now things become very obvious from here. So for instance, if you were to answer this query, the original query where we took the product of the cardinalities, right? So the optimization goes something like this. We will just use the fact that summation distributes over multiplication, and you will push the summation over z inside of the product, right? And once you have this push, then you can materialize the subquery into a quantity, say T1. And once you have T1, then you can do the same with, you know, push the summation over y, and then have this T3, this blue T3, and then orange T2, and multiply the three together. So this is how mathematically you would kind of explain the query plan that is actually is a correct query plan. Now, in practice, what you have to do is to map back from, so this is still an algebraic representation as a little sum product subquery, right? And then you have to map back to your original, you know, relational algebra query or whatever the original language it came from. So you just map to this IR, you do optimization under this IR, and then you map it back. But so the mapping has to be kind of, you have to be able to undo the mapping. And of course, we can also cook up the same thing, but over, say, min plus. So a cute puzzle that you can do is to write the original query, but in the min plus semi-ring. So like, you know, pose the same puzzle that I posed in the beginning, but just write it as compute the min over xyz of rx plus sy plus tz. Then it's not as obvious as multiplying the cardinalities, right? So if you want to take the minimum over the sum of three things, and you can take the minimum of the first thing, you add the minimum of the second thing, add the minimum of the third thing, and it's not as obvious anymore as multiplying the products. But the underlying algebra is identical.
You were saying that you have to undo things. I'm assuming that you have to undo them because the actual query executor is not using this IR, right?
That's right, yeah, exactly. I am assuming that whatever thing you want to kind of evaluate these subqueries on, not on this IR, but you might also have the same IR to execute things on, then in that case you don't have to undo it. But this IR is not universal, I would say. So one thing that this doesn't do very well with is, say, you have a summation over union, for example. And it doesn't map very well to this IR, right? So that's a case when you kind of have multiple semi-rings nesting in one another. So you basically will have to map it back to an IR that can represent all of the operators, and then you map it back to that form, evaluate it, and then, because here this is only just one sum and one product over one semi-ring. Okay, so so here this is an interesting, little more interesting example. So this is the case when we are counting our x, you know, the triple x, y, and z, for which x is less than y and y is less than z. Right? So let's try to play the same game again. So the first thing we'll do is we're gonna push the summation over z inside, right? But if you notice here, I'm cheating a little bit. If we use the same strategy as we did in the previous example, S of y would not have been in this purple subproblem, right? We would have factored out S of y outside of this purple sum, right? But if we were to sum over OZ for which you know, y is less than z, you need y to be grounded. It has to be in some relation, because this relation is infinite. Right? So we cannot put S outside of the sum in order to evaluate this subquery. So when coming up with a query plan, you will need a cardinality estimator to estimate what is the time or the cardinality of this the subquery, and you do this little projection from the outside to the inside in order to construct the right subquery. Okay, but once you have the subquery, so this is essentially the same query as I showed in the example, then now you can also evaluate this subquery. But in this case, there's no more pushing, because even if you push the summation over y inside, you can't really factor out R of X out of that sum. So this is kind of the atomic query already. Right.
I'm assuming this is to do with like the running intersection property, if you actually do the hypertree decomposition of the query. The property that the y has to be grounded is something like that.
No, it's different. So when you construct the tree decomposition, you also have to decide which relation goes into which bag. And what this is saying is that in the tree decomposition, the S relation has to be covered by the purple bag of the tree decomposition. And that decision has an effect on the query plan that you will produce from the tree decomposition. So because you could have, let's say, assigned S to the black bag, right? But that will not be a valid query plan.
Could you assign it to both? This is what we discussed a while ago here in class. You could assign it to both bags. Right?
Yes, in some cases, it's a good idea to assign to both bags, because technically, the more stuff you assign to a bag, the more selective the bag will be, right? The size of the bag can only be reduced. So if you can, then assign them to all. However, in practice, you know, you have to balance that, right? Because the more you join, the slower, sometimes the slower the query can be, and you need other information to decide what to do. Okay, so I'm not going to belabor the point. This is another example on the three path counting. It's the same type of thing. You can do variable elimination and have different subqueries in the blue one, the purple one, and so on. And in database jargon, these are called aggregation, projection, predicate, pushdowns, basically. Oh, actually, this is exactly the an example of a predicate pushdown, right? We're pushing the predicate of S into this summation. And it is all semi-ring. Okay, so I would like to introduce one more idea. Actually, how much time do I have?
Until 12:25.
Oh, okay, so I have plenty of time. That's great, thanks. So I want to introduce one more idea, and this may not be obvious. So consider the following query. So the shape of the query is, I have kind of a big relation, BCDE, and then there are two triangles sort of hanging off of it. So I have BC connected to A, and then DE connected to F. Okay? So a quadruple of relation T, and then there are two triangles, one on the F side and one on the A side. Okay? And here we are looking at a sum product query. Yeah. So let's try to do variable elimination and see how far we get. So I'm kind of jumping ahead, but suppose that you are summing over F, right? And let's forget about this yellow thing for a moment. If we factor anything that, factor out everything that does not depend on F, right? then we would factor out R, S, and T because they have nothing to do with F. And then we will join W, E, F, and V, D, F. Now, if you ignore this yellow factor, then this will run in quadratic time, right? Because creating the blue subquery already can run in quadratic time in the worst case. However, we also know that the variables E and F are actually bound, no, the variables E and D are actually bound from the outside of the subquery. Okay. And they can be used to actually lower the complexity of the query. And so what we do is we take this factor T and we project it back into the subquery. This projection just says that if D and E is in T, then this factor, this yellow factor, is going to get a value of 1. If not, it will get a value of 0. It is an indicator projection. Okay. So indicator projection can be computed in linear time in T. Okay. But the nice thing is that once we have done this, then now the worst case optimal join effect is now this blue subquery can be computed in n to the 1.5 time. So we lower the complexity by adding more stuff to it. Okay.
Just to clarify, so the indicator projection is kind of keeping the multiplicities. You're not like swatching the multiplicities of D&E, right?
That's right. Yeah, yeah. So the reason that we only want this indicator projection to take values 0 and 1 is so that we are not, because we're taking a sum, so we don't blow up the sum. So semantically, it's the same query.
So does that require you to like build an index over it, or do you just need to include it, or
It's you can literally compute the projection, like exist B and C for which D and E. So you project the relation down to the 2 columns and use that temporary to join with W and V. So we are creating a triangle where it doesn't exist in some sense, right? We're creating a triangle, but this helps with lowering the complexity down to n to the 1.5. And this idea is exactly subquery decorrelation. So if you think about this blue subquery, it actually correlates very strongly with the stuff outside of the subquery. And so we decorrelate it by projecting things from the outside back to the subquery to lower its intermediate size. Okay, pause for a moment and see if any other comments on this idea. Right, so once we computed the blue subquery, then we can, go on with our lives. And you can kind of overdo things a little bit because asymptotically speaking, projections are cheap. You can always project because, the time it takes to project is linear in the input. So you could, consider doing things like this. It's not going to increase the exponent in the query plan, but always doing this will slow things down in practice, right? So you have to kind of juggle a little bit with the cardinality estimation statistics on these plans. But ultimately, for this example, the whole thing comes down to n to the 1.5. And what that means is that the fractional hypertree width of this query is 1.5.
I guess I assume you guys have built an optimizer to make these decisions. Like, what goes into your?
Yeah, so we will need cardinality estimations, basically. So we have to make decision based on, the information theoretic bounds. I think Dan has a lecture on or two on that topic. essentially you need to know whether, or at least in theory, whether or not doing this projection is going to lower the worst case size bound for this blue subquery. And the more statistics you have, then the more that estimate is going to be, trustworthy. But all estimates in practice can still blow up, right? It's kind of operating under incomplete information.
But as you're saying, you could always do it, and worst case, you're, adding some linear overhead.
That's right. Yeah. Yeah, but linear overhead on
Really bad.
yeah, it could be pretty bad. Yeah. Okay. Now, so so far we have been talking about variable elimination. So this is what you would get if you open a graphical model textbook. They would do something like this exactly, except for this indicator projection, which mostly only apply to databases, because in graphical models, all of these domains are very dense. So there's no value in projecting, because all of the D's that are in T are also in V. All of the E's are in T are also in W, and they are kind of cross product of things. So there's no value in doing this indicator projection when you reason with graphical models. But in databases, things are a lot more sparse. They tend to be not cross product. Now, also in graphical model textbooks, they will move on from variable elimination to message passing. So that's where our 3D compositions come in, right? So another way to view these query plans is by 3D composition. So the first thing is we construct a 3D composition from the query. And then you have to decide where the root of the 3D composition is. In this case, the root is just ABC, where you compute the output. And then every bag of the 3D composition is going to send a message to the parent bag towards the root of the tree. And that message is exactly our subproblem, right? So in this case, the first subproblem is this message M1. The message is just another sum product query. Every message is a sum product query. The message itself is the head of the query, right? So you get M1, and then you will use this message as an input to the next bag in the 3D position, along with some of the actual inputs. So here you construct the next message and you send it along, and finally you construct the output that way.
Quick comment here. So I'm sure you remember Yannakakis algorithm. And in Yannakakis algorithm, we had to do the semi-join reduction before we do the full join, if we wanted the full join. And the semi-join reduction has two passes, from the leaf to the roots and then back from the roots to the leaf, in order to make sure that every relation is reduced. But if you have only a Boolean query, you only want to check if the join is empty or non-empty. You only need the bottom-up semi-join reduction. And when you semi-join reduce a root, then you know whether the query is empty or not. This is like a Boolean query, because we are completely aggregating away, we are projecting away all the variables. So this is like a semi-join reduction from the leaf, from the fluum, all the way to the root. This is why these kind of queries are so simple. I mean, simple. This is the connection between Yannakakis and.
So does this also mean that if we, there's nothing stopping you from using this framework to execute a sort of full query where you're not projecting anything out? I guess you're losing a lot of, you'll be worse off than Yannakakis.
Right. So using this framework, you can do, so in graphical model, this step is called calibration. So you calibrate the 3D composition, which is exactly like Yannakakis. You pass messages up and down the tree. And now all of the factors in the model are calibrated. And you can use it to answer, like, for example, singleton marginal queries or something like that. So it's exactly the same algorithm and also the same mathematical justification for it.
But I guess my question is, like, if I happen to have a full query or like a full-ish query, or I'm not aggregating everything away, is there a way to get Yanakakis-like behavior inside this framework by, adding a bunch of extra terms or something like that.
Yes, so you can do exactly this, right? You can do this message passing, but in that case, you are not eliminating variables. You are only eliminating the dangling tuples from. So there's a way in the FAQ paper we explain how to kind of set it up. It's a different semi-ring though. It's not like a Boolean semi-ring. It's a semi-ring on sets.
Okay,
Yeah.
I see.
Yeah.
So if you just use the setting ring, you sort of do the same thing, except you've not lost anything.
Exactly,
because
yeah.
You haven't actually detected.
Precisely, yeah. Yeah. Okay, and I still find it fascinating that these two ideas actually came out at roughly the same time, and it's really the same idea. Message passing is a very powerful idea, and I would like to claim some credit for database people because Yanakakis came up with this in '81, so maybe one year beforehand. Okay, now, for this, you could have done the elimination in slightly different way. You can eliminate F and then A, for example, and all that does is it will change the tree decomposition. Yeah, so effectively, every tree decomposition and every variable ordering, there's kind of almost a one-to-one mapping between the two. Okay, so now that we have seen this pretty kind of powerful framework for representing queries and also for optimizing queries, let's kind of try to generalize that a little bit. So the first thing we'll do is we'll generalize the representation, the sum product queries into something a little more general, so it can capture a larger class of queries. So here's the functional aggregate query representation. So in the sum product representation, we are working over only one semi-ring. So there's only one sum and one product. Okay? But now let's say we want to do this summation over product, over max, over product inside. So we would like to kind of interleave things a little bit. Yeah? But of course, we have to restrict, what we are allowed, and here are the restrictions. So first of all, the query that we are working on will have a product inside, just like in the sum product case. So there's the innermost operator has to be a product, and that product is over all of the input k relations or input factors, right? And there's one for every hyper edge of the query. And now let's look at the marginalization operators. So we are going to marginalize away variables. The thing that will make it a little more general is that we are allowed to use different summation operators. So in the previous case, we were only allowed to use sum, but now we could, for example, say sum and product and max, for instance. Okay? So we are allowed to interleave operators. Now, but what operators are allowed, right? So in this case, there are two types of operators. So each of these are called an aggregate operator. They either will have to form a semi-ring with the innermost one, with the black one here. So for example, max product or sum product, they are allowed, right? So you could have max and sum interleave. Or the thing that's kind of also more interesting is that this aggregation can also be the product itself. So you could have max and then product and then sum and max product and sum. They can interleave in any way. Okay, so let's look at a few examples on why this is helpful in capturing some problems. But is there any question on kind of the form of this query?
Maybe we'll get to this, but like, this is a other like more like tree structured queries where there's like sibling relationships from different scenarios. Does that make sense? Because this is like very nested, like there's one product that you're just, summing over with different sum operations, but you can imagine a sort of bushier query, if that makes.
Yeah, good point. I see where you are getting at. So it's entirely possible for the product inside to be somehow uncorrelated. And then you could kind of make, you're not forced to follow this ordering of marginalization. And yes, we can look at the structure of this hypergraph and then do this decomposition correctly.
Yeah.
And that's part of the query plan.
Right.
Yeah.
And so first of all, it's very cool and surprising that it works across these different addition operators, but that begs the natural question.
That's right.
What about the different multiplication operators?
Yes, yeah. So I don't have a generalization to different multiplication operators. Yeah, but in the query plan, you will see that sometimes we can interleave these sums in a different way than the input query. So we'll look at some examples.
Just a clarification, is the commutative requirement a new thing, or have we been assuming that the entire time for the previous stuff as well?
We have assumed that all of them were communicated. Yeah,
Previous.
yeah, good question.
We did this in the lecture too, considering, so yeah. Commutative thinking.
But I mean, we were sort of watching, we were doing the optimizations by hand algebraically.
Mhm.
And I mean, if you wanted to work with a non-commutative semi-ring and you just didn't commute the terms, where I assume everything would still sort of work out. No, I mean.
Exactly, yeah,
Yeah.
yeah. So in fact, this would be an example of that, right? So if in general, max and sum do not commute, right? So if you put them in different semi-rings, they cannot commute at all. So you can commute the max together if they were next to each other. And then same with the sums. But sometimes you can move things if you look deeper into what's inside of this square.
Yeah.
Okay, so here are some silly examples. Obviously, Boolean conjunctive queries can be expressed this way. Or let's say sharp CSP. So you want to count the number of solutions to a CSP problem, then it's obviously, so this is already true in a sum product case. So I'm not going to go through these examples. Let me give some examples that need a power beyond sum product, like you need at least 2 semi-rings. Oh, I don't know if you know this, but matrix chain multiplication is one such query, right? Where you marginalize away all of the common rows and columns, and you keep only the first rows and the last columns, and marginalize away anything else. Okay, so quantified conjunctive query. So this is the first example where we need more than 1 semi-ring. So in logic, you can write a query like this, where you have a conjunction of atoms inside. So this is our product operator. And then you have a series of quantifications, of quantifiers. So you could have, let's say, for all and exists, right? So basically for all exists over a series of variables. So you can model the problem this way. This will be a functional aggregate query over the following, where you do the following map. Let's see. So there will be 2 operators, okay? Maximum operator and a multiplication. So these aggregations will either be max or product. Yeah? And the only difference is that we are going to replace existential quantification by max and for all by product. And the reason is that if there exists a 1 in a series of zeros and 1, if there exists a 1, then that means that the maximum value is 1. If there's no 1, then the maximum value is 0. So max over 0, 1 is precisely the same as existential quantification. Right? And then the for all, that means that in a series of zeros and 1s, if all of them were 1, then that means the product is equal to 1. So that's the mapping. And moving on to real numbers, the problem is more powerful for sure. So now we have quantified conjunctive queries captured in this with this language, right? Right. Any questions so far? This is the first example of non.
So this is first order logic with arbitrary quantifiers.
Right.
For all operators. QH should be QI.
This gives you arbitrary positions of, I guess you can reshuffle things around. Like, I mean, you have arbitrary alternation, but I guess you, yeah, that makes sense.
Is this the plan list to replace Williams with like probabilities or something? Is it query? Because like, why can't you just use for max and then and for times? I guess like you're saying that the innermost thing is like a real value.
Yeah, so here I'm mapping, you know, all of the atoms into kind of K relations over 0, 1. It's just one way to do this mapping, and I'm sure there are other ways. Yeah. I guess the reason I want to do this is because of the next example, which is that now let's say we don't want to just know whether or not something is true, but we want to count the number of satisfying solutions. So this would be sharp QCQ problem. So in this case, we not only we need the max and product, we also need a sum operator. So let's say you would like to count the number of satisfying assignments, right, over x1 to xf. So here now you have sum over x1 up to sum over xf, and then the part that is inside is mapped exactly like the same as before.
So I guess in the case where your different summation operators do not compute, right, then in some sense nothing special is really happening, because it's like you could just leave those free, run the query, and then change your simmering once the query's done, and then sum later.
Yeah, in general, if the thing inside here is very dense, then there's nothing you can do. But if you have this product being a product of singleton factors, then even if you have a sum over x and then a max over y, and then Rx and Sy, let's say, then because they are decoupled, so even when the operators do not commute, but because of the independence that you can see from the inside of the query, they can commute. Yeah, so let me try.
If you turn your camera on. And I think we are out of luck with the markets because people just keep moving. Yeah, I don't see anyone. Really nothing. Sorry.
Okay, yeah, no worries. Let me repeat the example. I think it's simple enough to kind of work out in our heads. Yeah, so let's say you have only two variables, x and y, and then you have a sum over x and a max over y, and then the inside is Rx and Sy.
Okay.
Right. So the product fully is factorized because it's Rx and Sy. Right. So in principle, the sum and the max do not commute. In general, you cannot commute the sum and the max. But because Rx and Sy are independent, then you can actually you can sum over x first, or do a max over y, or vice versa, and it will not. It will still be fine.
I see. Okay.
Yeah. So this decoupling is something that we exploit in coming up with a query plan, even when the operators do not commute. And that's based on tree decomposition, because tree decomposition is precisely designed for that purpose. Because if you condition on a set of variables of a tree decomposition, and all of the children bags are independent, they are conditionally independent. And so if they have different aggregation operators, they can be interleaved in any way. Okay, so there are many more examples, form domains that you may not think, or some product or FAQ queries like computing the permanent, or let's see, list recoverable codes, things like that. They're not at first glance, or discrete Fourier transform, things like that can be mapped to this language. Okay, now, so let me give you kind of the skeleton of the general algorithm where we have multiple different semi-rings that can participate, right? So let's go back to variable elimination, but in a more general sense. So let's say we have already decided on the ordering of variables that we want to eliminate, right? So then what we can do is, if we were to eliminate the nth variable, so a summation over xn, then what we can do is we will factor out all of the factors whose support does not contain n. And then, of course, this is the least we have to do, right? We have to keep inside all of the factors that do contain n, because that's how you will sum away one variable. But as we have discussed just now, the idea of indicator projection is important, right? So you will project things from the outside back to this subproblem by doing a linear projection pre-processing step. And so the factor becomes a little bit more complicated with some projections. I'm not going to bother going over the notation. It's essentially anything that has to do with the support of this back in the treating position will be involved in the projection. And then you can measure this using the AGM bound on everything that is involved. So the cost of this query is the AGM bound on this back. But in general, you should think about replacing this AGM bound with some kind of cost estimator. So AGM bound is just one way to do cost estimation. It may not be the best way. Okay, so that's it. So the the runtime of this algorithm is going to be a summation over all variables, and then the cost will be kind of the worst case optimal join algorithm used to compute this back. So that's why it's a sum over the AGM bound. But if you have a better join algorithms or whatever, just consider replacing them with the right cost function inside. So here we can get things like, I don't know, you can do PGM inference in fractional hypertree with time or something like that. But as I said, this is a meaningless result in the PGM world because of the density of the factors. Okay, so this is not very interesting. We can get like fractional hypertree width this way, and so on. You can solve, for example, quantify a free sharp conjunctive query in polytime. This was a result from Reinhardt and Duran and Mengel in 2011 and 2013. It's very nice to see kind of just one single algorithm, and you can go over historical papers one by one, and you see that they are essentially doing this algorithm. Okay, so let's look at, let me see. Sorry, what I meant is this is the same algorithm, but now over an FAQ query. It's not just a sum product query anymore. So we could have different aggregation operators. Yeah. So let's say we have decided that this aggregation operator is the one we are going to apply first. Then there are a few cases. So if this operator is a semi-ring, form a semi-ring with the product operator, then we do exactly what we have done before, right? So we just factor things out and compute it just like before. So what is different though is that if it's not a semi-ring, then it will have to be identical to the product operator. So just like in the case of for all, right? So what do we do now? If it is a product, that means that these two operators are identical, then this is a much easier problem, it turns out. Because, if you just focus on this, product and product will commute in any way you want, right? So all we do is the following. We are going to factor out of this sum, which is the product. We factor out all of the factors which do not involve the variable xn, the one that we are eliminating. Now, because we are supposed to multiply with xn itself, like the domain of xn many times, right? That's what the aggregation operator was over, is over the entire domain. That means that every factor that we factored out will be multiplied with itself, the domain, many times. Okay, and that's really is the only difference. Is there's no need to do indicator projection or anything like that. You just raise these factors to a certain power. Now, in most queries, in practice, though, the product operator is idempotent. So, like, if you take a product over 0 and 1, then 1 times 1 is 1. You are not going to get new values, right? So if it's idempotent, then you don't even have to raise this to a power, because you multiply something with itself multiple times, you will get exactly that thing back. So in most cases, you will not have to raise this to a power, just have to factor things out. So that's a much easier operation to do than summation. So in some ways, for all is easier than exists. Okay, so that's the algorithm, and from there you can get a few other results, like doing sharp QCQ in certain amount of time and so on. So what I skipped over is how do we decide on which variable ordering to do, right? So that's actually the bulk of the work, is like finding the optimal variable ordering. So let me just give you kind of the schematic representation of what the technical contribution is of the FAQ framework. So it goes like this. I'm going to skip this slide, just give you kind of the high level idea, because we have about 3 minutes left. This is my last slide, technically. So
like 13, 20, 10,
Oh,
10
okay.
10 minutes.
That's great. Yeah, so then let me go through the slide. So the framework goes like this. So we are given a query, an FAQ query, or FAQ expression, sigma, and we want to compute an output factor or output head phi, right? So the algorithm is going to do variable elimination, so it creates a query plan. Now, each of the subqueries is going to be answered by what I used to call the outside-in algorithm, which is worst-case optimal join. So every back in the 3D condition is answered. You compute a message, send it up to the parent back. So it's an incarnation of worst-case optimal join, right? So inside-out is like bottom-up dynamic programming. And then the outside-in algorithm is backtracking search, because you can implement worst-case optimal join with backtracking search. Okay? So it's kind of a duality between these two classes of techniques. And so the runtime of the query is a function of the variable ordering, the sigma, at which we decided to eliminate variable, right? So the complexity is captured by something called the FAQ width of that variable ordering. Okay? But I haven't told you how to decide on what variable ordering to use. But if you give me the variable ordering, then the algorithm will run in that time. It's a function of the permutation of variables. Okay, and this is the FAQ analog of the fractional hypertree. Okay? So the measure is exactly the same. Okay, then the next question is, how do we search for the best one? So that's the main query optimization problem. So the approach goes like this. So the first thing we have to define, at least conceptually, is that given an FAQ expression, what are the semantically equivalent expressions? So if it was only one semi-ring, then all n factorial permutations are possible. If there are multiple semi-rings, then it's not obvious anymore, right? Now, it's true that if you have the same operator repeated next to each other, then you can permute them. That's easy. But in some cases, you can look at the query structure, like in the Rx and Sy example I mentioned, where the query itself has kind of independence property. Then you can use that. You can exploit that to say that sometimes some permutations are possible, even when the operators do not commute. So we have to determine the set that's called EVO, equivalent variable orderings of phi. So here's one example. Actually, I should have just pointed to this one. It may not be obvious, but if I, given these two queries, these two expressions compute the same thing, even when sum and max do not commute. Okay? So here we, in one query, we have summation over x2, x1, x5, and then a max over x4. Okay? So what I'm claiming is that you can permute max and the last max and the previous sum just by looking at the structure of this query. And the reason for this is because if you condition on 1, 2, and 3, so if you were to fix the three variables, x1, x2, and x3, then 4 and 5 are independent. So if you set x1, x2, x3 to be constants, right? So now you have a factor on x4 here, and then another factor on x4, and then you have a factor on x5, right? That's the last. So it's the product of two functions, one of x4 and one of x5. And they're not connected by anything. So now you can swap the operators. You can do the sum and the max, or max and the sum. Okay, so that's kind of the space of equivalent variable orderings that we can explore in order to choose the best one. Right. So from this space, we will have to choose a sigma star that will minimize the FAQ width over this space. And then once you have chosen that, then you can run the variable elimination algorithm with indicator projection, and the runtime will be optimal. Okay, now unfortunately, computing this problem is NP hard in query complexity. So if in data complexity you can do anything you want, just do n factorial possible permutations. But in practice, n is like 50. You cannot do 50 factorial. So you have to do something. There's an approximation algorithm. So what we kind of try to characterize this set by constructing something called the expression tree from the input sigma. Is basically based on the same idea. So we have sum, we have max, we have product, and so on. So you kind of construct the expression tree and put the operators at the right places in a tree to capture the fact that some of the things are conditionally independent. So if you condition on say x1 and x4, and everything else is independent, which means that you can evaluate them independently from one another. So that's kind of a way to capture this EVO. There's some proofs involved, but effectively that's what it is. So once you have this expression tree, then you can kind of show that every linear extension of this poset is an EVO and vice versa. So instead of optimizing over the EVO, you optimize it over this expression tree. And once you have that, then the next thing is to construct a 3D composition that will respect the partial order from this expression tree. So it's not an arbitrary 3D composition anymore. It's a 3D composition under constraints. And the constraints are basically coming from the fact that you cannot permute operators in an arbitrary way. And once you have that 3D composition, then the game is use GYO elimination to come up with the variable ordering and get the result out. And the proofs to show that you can get the best possible approximation ratio out from this framework. Yep, so that's all I have for kind of a generic query plan for answering inside-out queries. I mean FAQ queries. And if you would like to learn more, I think the FAQ paper was this one. We drew a lot of inspiration from the paper by Hubie Chen and Victor Dalmau on variable elimination over quantified conjunctive queries and so on. And of course, inspiration from variable elimination and graphical models literature. That's it. Thanks.
Thank you. Folks, before we let continue.
Go ahead.
So how faithful is the previous slide that we saw to, sort of what actually happens, say I have relational AI, and or maybe what should happen? Like, is this the right answer for how, if I was to build a database from scratch tomorrow, right? Is this the way we build it?
Yeah, so this would be a very robust way of building an optimizer, I would say. The main thing is cardinality estimation, cost estimation. So when things go wrong is typically because the cost estimate goes wrong.
Do you think that's true in any
That's right.
optimization framework? Do you feel like this framework is more brittle to poor cardinality estimation in some way, or?
I think our design philosophy is for the optimizer to be more robust. And so all of the worst case optimal join or worst case information theoretic cardinality estimation are designed so that you don't run into a really bad query plan. So I do strongly believe in this framework for building a really robust optimizer. It may not be the best optimizer out there in the millisecond time scale,
Sure.
But it's designed to be robust.
And what about optimizing outside in, which is the sort of the workhorse that makes this part go?
That's right.
It has its own variable ordering problem.
Exactly. Yeah.
Different, but are there similar shapes in terms of how you optimize for that, or is that?
Yeah, so that's precisely the another problem where cardinality estimation plays a huge role, right? Because if you want to decide on which variable ordering to run worst case optimal join on, you will need to kind of select the most selective variable first. Because once you have that binding, you will rule out a bunch of results in the space, and then you get the next binding and so on, and all of that is done through cardinality estimation.
And it kind of sounds like it would be interesting to talk about how the query optimizing executor works in REI.
Yeah, sure. Yeah.
We have time. If you need to give a lecture.
I may not have time this semester. I can give an online, an online talk. But yes, even constructing the 3D composition is a non-trivial. I mean, it's easy on paper always, but in practice, it's not easy, right? So constructing the 3D composition and also coming up with a variable ordering, and there are a lot of constraints. And how do you even represent? So in a traditional query, optimizer, what you have to do is you have to represent a collection of query plans together, right? And there are exponentially many of them. Certainly, you don't want to store them. So same thing with variable ordering. So you don't want to store all of variable ordering. So what do we do? So the representation and then how to search for the best one. Those are interesting.
Earlier you were talking about, like, there's a fallback in the case that, you know, you can't get things in the framework, but is it, maybe I missed this, is it as coarse grained as that? Like, a couple slides ago, you had this sort of like if else, right? You know, if it's a semi-ring, then we can do this, if it's not a semi-ring, but plus two times, we can do that. If it's idempotent, we have another thing. Is there an else there that, like, you know, doesn't take you outside the entire framework, but allows you to handle a single, you know, summation operator that you don't know anything about without breaking everything else?
Yeah, it's the answer is the same as the previous one. Basically, if you have an operator that doesn't form a semi-ring, then you effectively have to collapse everything into one factor. Yeah, so there's no factorization anymore.
And then, like, in that if else tree, because that's sort of like the heart of, you know, what is making FAQ work, I feel like, it's like, you know, if it has this algebraic structure, we're allowed to do X, Y, Z, like, what are the other things that we should be thinking about putting in that if else tree, right? Like, if it's a semi-ring and, you know, it's, you know, absorptive or whatever, like, you know, are there other algebraic properties that would allow us to do, you know, cooler, trickier things than that? Is that something that there's work on, or?
Yeah, so if you would like kind of open problems, so semi-rings is only one algebraic structure, right? You can think about like fields or groups, you know, exploiting some symmetries. There are certainly cute examples where if you exploit the symmetries, you can speed up things significantly because there's just so much symmetry in the data, for example. To cut down on the computation. And I think the most interesting that open question that is, I think is a low-hanging fruit, but I'm not 100% sure, is exploiting a ring structure. So it's just like a semi-ring, but now you have a minus sign, right? So what you can do is to overcompute and then subtract. And in some cases, that will give you an asymptotic speedup.
How well does this compose with things like physical data structure? Multiple nodes and all these.
Yeah, I don't operate in that
This is like
mindset.
simple thread.
Yeah, so we decompose it into kind of underlying join operator underneath, and then you know you can do scale out and single, you know, at that level.
Okay.
Right.
Let's come.
Yeah, thank you.
The plan for Thursday is to start the development iteration. Any question?